Hello, everybody. Glad to see you again. And today's we have our lecture number 3 on avionics engineering. And the topic of today's lecture is helmet-mounted display. You know, the advantages of heat-up visual presentation of flight and mission data by means of a collimated display have been explained in the preceding lecture. The HUD, however, only presents the information in the pilot's forward field of view, which even with a wide FOV holographic HUD. I hope you remember some abbreviation. Okay, nice. And holographic HUD is limited up to about 30 degrees in azimuth and 20 to 25 in elevation. Significant increases in these FOV are not practicable because of the cockpit geometry constraints. I hope you understand it. Yeah, we have some specific point of view. The pilot requires visual information head-up when he is looking in any direction. And this requirement can only be met by a helmet-mounted display, HMD. And this figure shows the comparison between HUD and HMD fields of view. In its simplest form, the HMD can comprise a simple helmet-mounted sighting system, which displays a collimated aiming cross or circle and some simple alphanumeric information with a typical FOV around 5 degrees. An addressable LED matrix array is generally used as the display source, enabling a very lightweight and compact HMD to be achieved. The helmet-mounted sight enables targets to be attacked at large or broadside angles, as will be explained. It should be noted that the term broadside is used to describe the direction in which the aircraft fore and aft axis is pointed and is based on the analogy of sighting through the bore of gun barrel mounted on the aircraft datum axis. In its most sophisticated form, the HMD can provide, in effect, a HUD on the helmet. This can display all the information to the pilot, which is normally shown on a HUD, but with the pilot able to look in any direction. Attitude information is referenced to his line of sight, LOS, line of sight. The HMD can also have a wide FOV ranging from 35 to 40 degrees for a fighter aircraft application, to over 50% for a helicopter application. It should be appreciated that the FOV moves with the head, unlike the HUD, and the larger FOV reduces scanning head movement in an HM display. It is still very useful, however, to allow peripheral information to enter the eyes so that the FOV is not just that the optic. The HMD also enables a very effective night or poor visibility viewing system to be achieved by displaying the TV picture from a gimbal infrared sensor unit, which is slated to follow the pilot's line of sight. The pilot's line of sight, LOS, with respect to the airframe, is measured by the head position sensing system. Such a helmet can also incorporate image intensification devices with a video output to provide a complementary viewing system. And now we have the topic called helmet design part. It is important that the main functions of the conventional aircrew helmet be appreciated, as it is essential that the integration of a helmet-mounted display system with the helmet does not degrade these functions in any way. The basic functions now: to protect the pilot's head and eyes from injury when injected at high airspeed. For example, the visor must stay securely locked in the down position when subjected to the blast pressure experienced at indicated airspeed of 650 kiloknots. The helmet must also function as a crash helmet and protect the pilot's head as much as possible in a crash landing. Right? Okay. To interface with the oxygen mask attached to the helmet, combat aircraft use a special pressurized breathing system for high G maneuvering, and to provide the pilot with an oral and speech interface with the communications radio equipment. The helmet incorporates a pair of headphones which are coupled to the output of the appropriate communication channel selected by the pilot. The helmet and earpieces are also specifically designed to attenuate the cockpit background acoustic noise as much as possible. A speech interface is provided by a throat microphone incorporated in the oxygen mask. In addition to the clear protective visor, the helmet must also incorporate a dark visor to attenuate the glare from bright sunlight. And the helmet must also be compatible with NBC for nuclear, biological, chemical protective clothing and enable on NBC mask to be worn. NBC, I repeat another time, it's a nuclear, biological, chemical. Any coating on the visor, when it is used for projecting the display, must not reduce the tail-core distance. That is, the distance at which the target can first be seen. The coloration effects from the coatings are also disliked by the pilot, and neutral density coating are preferred. The optical system must not provide any visible business line. For example, should the two halves of a binocular system about each other. This is to eliminate the possibility of such a weakness line, even in vertical, being mistaken for the horizon during extreme maneuver. Integrating an HMD system into the helmet must thus consider the communications and breathing equipment requirements, the protection, comfort, and cooling aspects, as well as the visual performance of the display. First generation HMDs have been based on modifying the effective bolting on the HMD optical module, display source, and associated electronics to an existing aircrew helmet. This can result in a build of a purge, and the total helmet weight can be high, and this is not good. Imagine you have a big G, and so how you can stay alive in this situation. More recent second generation HMDs are totally integrated with the helmet design, starting from a clean sheet of paper, and optimized to meet all the above requirements for the minimum overall weight. The combined mass of the integrated helmet and HMD system must be as low as possible to reduce the strain on the pilot's neck muscles during maneuver. Modern conventional aircrew helmets weigh about 1 kilo or 2.2 pounds, so that the weight the pilot feels on this head during a 9-gram turn is equal to 9 kilograms or 20 pounds approximately, and this is just acceptable. The typical weight for an integrated helmet incorporating a binocular HMD system is around 1.7 to 2.5 kilos or up to 5.5 pounds approximately. This is limited by the current technology, and lower weight is sought. The helmet center of gravity should be in line with the pivoting point of the head on the spine, so that there are minimal out of balance moments exerted on the neck muscle. Yes, imagine this. Okay. The moment of inertia of the integrated helmet system about the yaw and pitch axis of the head should be as low as possible. This is to minimize the inertial torque experienced by the pilot due to the angular acceleration and certainly deceleration of the head and helmet is scanning for the threads from behind or above. Peak ahead, motion rates of 30 degrees per second can occur in combat. The helmet must fit securely on the pilot's head and not move about so that the display is visible under all conditions, and the pilot's LOS can be inferred from measuring the attitude of the head with the head tracker system. The HMD optical system must be rigidly fixed to the helmet with adequate mechanical adjustments to accommodate the physical variation within the normal pilot population, interocular distance, and eye release. There should be at least 25 millimeter or 1 inch clearance for eye release between the nearest optical surface and the eye. The display is only fully visible when the eyes are within a circle of a given diameter known as the exit pupil diameter. The center of the exit pupil being located at the design eye position. The exit pupil diameter should be at least 12 millimeter or half inch approximately. It should be noted that the helmet will be pressed down on the pilot's head during high maneuvers as the helmet lining is resilient, and hence the need for a reasonable exit pupil so that the pilot can still see the display. Another subtopic today's lecture is called helmet-mounted sight. A helmet-mounted sight, or HMS, is conjugation with a head tracker system provides a very effective means for the pilot to designate a target. The pilot moves his head to look and sight on the target using the collimated aiming cross on the helmet sight. The angular coordinates of the target sight line relative to the airframe are then inferred from the measurements made by the head tracker system of the attitude of the pilot's head. In air-to-air combat, the angular coordinates of the target line of sight, LOS, can be supplied to the missiles carried by the aircraft. The missile heads can then be sleeved to the target LOC line of sight to enable the seeker heads to acquire and lock on the target. Typical seeker head needs to be pointed to within about 2 degrees of the target to achieve automatic lock-on. Missile lock-on is displayed to the pilot on the HMS, and the audio signal is also given. The pilot can then launch the missile. This enables attacks to be carried out at large of boresing angles, giving agile missiles with the high G maneuvering capability. The pilot no longer needs to turn the aircraft until the target is within the FOV of the HUD before launching the missile, and this is very, very positive characteristic. The maximum of foresight angle for missile launch using the HUD is less than 15 degrees, even with a wide FOV HUD, compared with about 120 with an HMS and highly agile missiles. This gives a major increase in air combat effectiveness. Factors of 3 to 4 have been quoted in terms of the kill probability, a very effective force multiplier in military parlance. The helmet-mounted sight can also be used to provide visual fixes for the navigation system by designating known landmarks and features, and does not require the pilot to overfly them. The display source on a simple helmet-mounted sight typically comprises a LED matrix array. This can range from a simple fixed format addressable array to, say, 32 times 32 matrix array, which can display some limited variable symbology, including alphanumeric. The display image is relayed to the visor by means of a compact optical prism and reflected from the visor into the pilot's eye. The surface of the prism has cylindrical and spherical curvature to correct optical error. Monocular systems are used which normally display the image to the right eye. The visor, which is of spherical profile, has a reflective coating patch on the portion of the visor in front of the eye, which acts as a spherical mirror and collimates the display image. Typical field of view for an HMS is around 7 to 10 degrees. The amount of display symbology of a simple sight is generally kept to the minimum, typically an aiming cross of circle and simple curing arrows up, down, left, and right to direct the pilot's LOS to array the acquired target, or a detected threat and missile status, like Nickolay. Another subtopic today's lecture is called helmet-mounted display. As mentioned in the introduction, the HMD can function as a HUD on the helmet and provide the display for an integrated night of wear visibility viewing system with flight and weapon aiming symbology overlying the projected image for the sensor. Also, monocular HMDs have been built with which are capable for displaying all the information normally displayed on an HUD. There can be problems with that is known as monocular rivalry. This is because the brain is trying to process different images from each eye, and a rivalry can occur between the eye with a display and that result. The problems become more acute at night, when the eye without the display sees very little, and the effects have been experienced when night flying with a monocular system in helicopter. It has been shown that a binocular system, whereby the system display is presented to the both eyes, is the only really satisfactory solution. And hence, current HMD designs are generally binocular systems. Miniature 2-inch diameter CRTs are currently used as a display source. The development of miniature high-resolution liquid crystal displays, LCDs, however, has changed this situation. HMDs excluding these devices are now being produced. Night viewing applications require the widest possible FOV. This is particularly important for helicopters operating at night at very low level, like 30-foot flying, net of the Earth. Missions taking every possible advantage of terrain screen. Binocular HMDs for helicopter applications have minimum FOVs of 40 degrees and FOVs of over 50 degrees have been produced. Fighter or struck aircraft HMDs generally have HOVs of 35 to 40 degrees, trading off FOV for a lower weight optical system. Helmet weight must be kept to a minimum because of the load exerted on the pilot's head during high G maneuver. A lower weight HMD system can be achieved by, one second please, can be achieved by the use of the visor projection system in conjunction with a high-efficiency optical design. This allows a standard spherically curved aircrew visor to be used to carry out the combiner and collimation function by the addition of a neutral density reflection coating. The visor coating provides high display brightness whilst maintaining high real-world transmission. More than 70% can be achieved with no coloration, and display accuracy is also insensitive to visor rotation because of the spherical shape and partial rising of the visor is possible. For example, to carry out the Valsalva procedure, it means is pinching the nostril and blowing to the equal of the pressure in the ear. The combiner and collimation function is thus achieved without adding additional weight to the optical system, as the visor is essential anyway. FOVs of over 40 degrees can be achieved with binocular visor projection system. The visor, however, is a long way from the eyes, and creating an extreme FOV is increasingly difficult over 60 degrees. The alternative IP system can give a larger FOV, but a very high weight penalty. Also, a binocular HMD is inherently a better solution for night or poor visibility operation. And there is a large market for a low-cost, lightweight HMD for fighter aircraft, which are primarily involved in daytime operations to provide a helmet mounting queuing and a sighting system. The lower weight and the cost achievable with a visor projected monocular HMD can make this a cost-effective solution in such application. Also configured for daytime use, such a system is capable of displaying video from a sensor, providing the pilot with an enhanced viewing system after dark or in a bad weather. It is appropriate at this point to discuss the use of image intensification devices, as these provide a night vision capability, which essentially complements an infrared viewing system. Each system being better in some conditions than the other is. The wavelengths involved are shown below. The image from the image transfer tube, IIT, is a phosphor screen, which emits green light in the center of the visual band, where the eye is most sensitive. Night viewing goggles, NVGs, incorporated image intensifiers have been in operational use in military helicopters since the late 1970s and in fast jet aircraft from around the mid-1980s. NVGs, or night viewing goggles, basically comprise two image intensifiers through which the observer views of the scene at night by means of a suitable optical arrangement. Image intensifiers are highly sensitive detectors, which operate in the red end of the visible spectrum amplifying light about 40,000 times from less than starlight up to visible level. It should be noted that special cockpit lighting is necessary, as conventional cockpit lighting will saturate the image intensifier. Special green lighting and complementary filtering are required. Most night flying currently undertaken by combat aircraft is carried out using NVGs, which are mounted on a bracket on the front of a standard aircraft helmet. The weight of the NVGs and the forward mounting creates an appreciable out-of-balance moment on the pilot's head and precludes the pilot from undertaking maneuvers involving significant G. The NVGs must also be removed before ejecting because of the J experienced during ejection. I hope you agree with this. A quick release mechanism is incorporated in the NVG's attachment. An integrated helmet design with the NVGs located near the natural pivot point of the head so that they do not create significant out-of-balance moments. Avoid this problem. NVGs can incorporate it into an HMDs and optically combined with the CRT display so that the clear video display overlays the image intensifier display on an accurate one-to-one base. Enable the two systems to be combined in a complementary manner. And this figure illustrates the basic optical mixing of IIT and CRT imagery. The image intensifier devices can be battery powered from a small battery carried by the pilot. This enables the pilot to see in pitch darkness conditions on the ground and walk out to the aircraft or helicopter without any lights being required during covert operation. And this figure illustrates the binocular HMD system with integrated IITs, which are optically combined with the CRT display. In the case of fighter or strike aircraft, the weight and bulk penalty of optical combining the IITs with the display optics has led to the adoption of image intensification devices, which image on the small CCD cameras. The output of the image intensifier CCD camera is a video signal which is fed back to the remote display drive electronics, where it is electronically combined with the symbology and display on the helmet-mounted CRT. This figure illustrates the concept of electronic combination of IIT and CRT. The advantage of this approach is that it maximizes the performance of the CRT display by removing the need to mix IIT and CRT imagery optical. The intensified imagery is not presented in a raster form, allowing the potential to enhance the night vision image, improving image contrast, and reducing some of the unsatisfactory characteristics of directly viewed IITs, such as image blooming. The ability to enhance the image contrast electronically allows the user to see undulation of terrain, such as featureless deserts not visible using conventional NVG. Similarly, a bright point source on light view by a conventional NVG results in a color effect and blocks out the surrounding scene. This effect can be eliminated, allowing the user to view clearly a scene containing bright sources of light, such as street light. The performance of current night vision cameras is, however, inherently lower in terms of resolution than that provided by the best NVG. Active development of helmet-mounted night vision cameras is taking place. Two developments are, first, the E-beam CCD, where the CCD is integral with the IIT vacuum tube. And second, the low light CCD camera, which dispenses with the IIT and promises a high performance with small size. It is likely to supply the other side vision cameras when it is fully developed. This figure shows the Eurofighter Typhoon HMD. This is a binocular visor projected helmet mounted display, which is used by the pilots flying the new Eurofighter type. It has a 40 degrees binocular FOV and has integral night vision cameras, which are electronically combined with the CRT. Clear or IIT imaginary can be displayed with flight and weapon aiming symbology overlay. An optical head tracker system is used to determine the pilot's LOS. This has a fast response and provides high accuracy. I hope you remember this abbreviation, LOS, right? Nice. A modular approach is likely to be adopted for helmet systems, with a common helmet shell and different modules for the different roles. Modules can be simply fixed to the basic helmet shell, which uses very strong but light materials and is made in a number of sizes, which are precisely fitted to the pilot by an injection molding process. The modules can range from a simple visor through a daytime sight to the top of the range system with image intensifier and CRT. The same helmet shell can be used for the helicopter applications with the appropriate module. The extensive optical and electrical parts can be replaced quickly and sent off for repair without the pilot losing his personified helmet. It should be noted, however, that a helmet with an integrated HMD system will be a relatively expensive piece of kit and will need to be treated with more care and respect by the pilot than the current aircrew helmet. Next subtopic today's lecture called head tracking systems. The need to measure the orientation of the pilot's head to determine the angular coordinates of the pilot's line of sight with respect to the airframe axis has already been explained. Right? It should be noted that the problems of measuring the angular orientation of an object, which can both translate and rotate, would be a fundamental requirement in other applications such as robotics. In fact, the solution for head tracking system can have general application. Space does not permit a detailed review of the various head tracking systems, which have been developed. Most of the physical effects have been tried and exploited, such as optical, magnetic, and acoustic missiles. Optical tracking systems work in a number of ways. For example, pattern recognition using a CCD camera, or detection of LEDs mounted on the helmet, or sophisticated measurement of laser-generated fringing patterns. Magnetic tracking systems measure the field strength at the helmet from a magnetic field radiator located at a suitable position in the cockpit. There are two types of magnetic head tracker systems. On AC system, using an alternating magnetic field with a frequency of around 10 kHz. And DC system using a DC magnetic field, which is switched at low frequency. Both systems are sensitive to metal in the vicinity of the helmet sensor. This causes errors in the helmet attitude measurement, which are dependent on the cockpit installation. These errors need to be measured and mapped for the particular cockpit and the corrections stored in the tracker computer. The computer then corrects the tracker output for the in situ error. The AC system is more sensitive to these errors than the DC system, which is claimed to be 10 times less sensitive to metal than AC system. The sensors and radiators for both AC and DC magnetic tracker systems are small and lightweight. Typical sensor volume is about 8 cubic centimeters or half cubic inch, and weight about 20 grams or 0.7 oz. The radiator volume is typically about 16 cubic centimeters or 1/8 cubic inch, and weight about 28 grams or 1 oz, excluding installation. Angular coverage of the magnetic type of head tracker is typically around plus minus 135 degrees and azimuth, and plus minus 85 degrees in elevation. Accuracy on or near bore side is generally within 2 milliradians and around 0.5% at large or bore side angle. A reasonable head motion box can be achieved, which is operationally acceptable for most applications. All the systems, optical, magnetic, and acoustic, have their individual limitations. Also, the magnetic systems are currently the most widely used. High accuracy at larger or bore side angles is attainable, however, with the latest optical system. Each system is notable for the complexity of the algorithm needed to sort out the signal from the noise and the man years of software programming in them. It should be noted that other errors could be encountered in measuring the pilot's direction of gaze apart from the inherent errors, which are present in the head tracker system. This is because the pilot's direction of gaze is inferred from the helmet attitude measurement. The pilot can, in fact, experience great difficulty in keeping the helmet sight on the target when subjected to severe low-frequency vibration. This can result from the buffering, which can be encountered at high subsonic speeds in turbulent air conditions at low altitude. The power spectrum of these buffeting vibrations can include significant levels in the 1 to 10 Hz frequency range, which the pilot is unable to follow and keep the aiming cross on the target. Tracking errors of over 2 degrees follow the keep the aiming cross on the target. As these have been measured under replicated buffeting tests carried out on the ground using tape-recorded flight data. Some specification of the vibration environment can be gained from the fact that a sinusoidal vibration of half G amplitude at frequency of 2 Hz corresponds to an up and down motion of plus minus 31 millimeters. It has been shown, however, that the pilot's gaze can still be maintained on the target while the pilot is experiencing low-frequency buffeting type vibration. This is because the contour of the eyeball and hence the direction of gaze, right, by the eye muscle has a much faster response than the control of the head position by the neck muscle. The eyeball servo has in fact a bandwidth of several hertz in control engineering terms. The sideline measurement accuracy can hence be greatly improved by the use of an eye tracker system, which measures the direction of gaze of the eye with respect to the helmet. The gaze angle relative to the airframe can then be obtained by combining the eye tracker and head tracker output. The eye tracker also offers advantages in high conditions when head movement is difficult, but the eyes can still move to look at a target. The basic principles of the eye tracker are very briefly explained in a bit later, as an eye tracker can also be used very effectively as a means of data entry, a possible development in future cockpits. Next, our topic today's lecture, HMDs and the virtual cockpit. The concept of a virtual cockpit, where information is presented visually to the pilot by means of computer-generated 3D imagery, is being very actively researched in a number of establishments, both in the USA and in the UK. There is no doubt, however, of its importance in the future and the revolutionary impact it is likely to have on the next generation of aircraft cockpits. The increasing use of remote piloted vehicles, RPVs, and their control from a parent aircraft or ground station is another future application for HMDs and virtual cockpit technology. It should be noted that RPVs, or remote piloting vehicles, could include land vehicles or underwater vehicles as well as airborne vehicles. A correctly designed binocular HMD is a key component in such systems because it is able to present both a display of information at infinity and stereo images to each eye so that the pilot sees a 3D image. It should be emphasized that the binocular HMD's optical system needs to be accurately designed and manufactured in order to achieve a good stereoscopic capability. The ability to generate 3D displays opens up entirely new ways of presenting information to the pilot and crew. The objectives being to present the information so that it can be visually assimilated more easily and in context with the mission. As an example, information related to the outside world can be reviewed head up, and information related to the mission and the aircraft health, and can be viewed head down using only one display system, namely binocular HMD. This figure illustrates the use of binocular HMD to implement such a system. When a head up, the pilot views the outside world directly or indirectly by means of a TV display on the HMD from a head's sphere gimbal electro-optical sensor. Another, say, infrared imaging sensor or love light TV camera or CCD camera. When looking down at the instrument panel, the virtual cockpit computer system recognizes the pilot's head down sideline from the head tracker output and supplies this information to the display generation system. The display generation system then generates a stereo pair of images of the appropriate instrument display on the panel, which corresponds to the pilot's sight line. And thus, looking down into the cockpit at the position normally occupied by a particular instrument display will result in the pilot seeing a 3D image of that instrument display appearing in the position it normally occupies. or a virtual instrument panel display. Carried to its logical conclusion, the normal head-down displays and instruments would no longer be required. Simple standby instruments of the get-your-home type would be sufficient to cover the case of a failure in the HMD system. Such a bold step, however, is still several years away from implementation in a production aircraft. Novel ways of presenting information to the pilot by means of the binocular HMD include displaying of a 3D pathway in the sky as a flight-directed display, which can be overlaid on the normal outside scene, or directly or indirectly viewed, or on a computer-generated outside world scene created from a terrain database. A God's eye view can also be presented, for example, what the pilot would see if he was outside the aircraft and looking down from the sky of the, say, 2,000 feet above and slightly behind this aircraft. Beam me up there, Scotty. The threat situation can be presented on such a God's eye view display, or enemy aircraft missile site, anti-aircraft artillery, AAA, sites or enemy radar sites. Threat zones defining the missile or gun range, radar field of view, etc. can be presented as 3D surfaces, so that the pilot can assimilate the threat situation on a single display. And this figure shows a 3D God's eye view display, which provides the pilot with a stereoscopic view of his helicopter, as well as its relationship to its proposed flight path. Further information can be provided by enabling the pilot to change his apparent position outside the aircraft. With advances in display technology, it is reasonable to anticipate lightweight, high-resolution color displays, which would be capable of providing a helmet-mounted color display of comparable quality to the current color head-down display. This, for example, would enable a color map to be displayed on the HMD. It is worth sounding a slightly cautionary note on virtual cockpit technology and the need for all the human factors issues to be addressed and satisfactory solutions achieved for any problem that may be encountered. Some programs have, in fact, been expressed recently on the physiological and psychological effects of prolonged viewing of commercial virtual reality systems, and the ability to the user to switch back to the real world immediately. Where quality stereo optics requires the visual processing part of the brain to make major adjustments to fuse the resulting stereo images into a 3D picture. To adjust back to normal real-world viewing can then take some time. The cockpit environment, however, is very different and requires frequent viewing of the outside world, whether directly or indirectly, by means of a head-steered gimbal camera system. The virtual reality problems referred to above may therefore not arise. The stereo quality of the optical system of the binocular HMD is also far higher than the current commercial virtual reality system. The hardware, in terms of the binocular HMD's graphics processing, symbology generation, together with the software to implement many of the virtual cockpit concepts exist today, also system integrity still needs to be established. The relatively slow adoption of the concept is due more to defense budget constraints in both the UK and the USA rather than technology limitations and technical risks. Mention should be made of the potential of what are referred to as virtual retinal displays, VRD, for future virtual cockpit. In such systems, images are not presented on a display surface, but instead are projected directly to the retina of the pilot's eye by a raster-scan laser light beam. The technology offers a number of advantages and is being actively developed by a company called Microvision Incorporation, Seattle in USA. The current technology of implementing a virtual retinal display involves lasers, optical fibers, and miniature vibrating mirrors for raster scanning the retina of the eye. Together with coupling optics, a binocular VRD thus imposes a significant weight delta to the film. At the present time, the miniature reflecting AM LCD is able to provide a lower weight, less complex, and lower cost solution for a fast jet HMD, where minimal weight is essential. The AM LCD display is not as crisp as a VRD, but is fully accepted. Next lecture will be about computer-aided optical design. And for now, I think it's enough for today. I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.